Hello, welcome to Material Science lecture. So in this lecture, we're going to continue our discussion on binary phase diagram, but this time we will talk about eutectic system. So another type of common and relatively simple phase diagram found for binary alloy is known as eutectic phase diagram. So the formation of what we call as eutectic alloy system is because there is only a partial solubility limit between the element that we are going to mix together. So remember, binary alloy means a mixture of two elements. So in this binary phase diagram, there will be a three single phase region exist. So we will have liquid phase and two types of solid solution. So in contrast to the isomorphous system, where we have a discussion in the previous lecture, only two single phase exist in isomorphous system, which is liquid, and only one type of solid solution when the molten metal completely solidified. So now let's have a look into this system. So hopefully by the end of this lecture, you would be able to understand what is eutectic system. You would be able to read and interpret the eutectic phase diagram. And also you would be able to write reaction for eutectic transformation for either heating or cooling. So it is important to know how to use these phase diagram in order to design a heat treatment process for some alloy that will yield a desired room temperature mechanical properties. So in eutectic system, similar to the isomorphous system, for binary alloy, it has two components, but this time they have limited solubility. So it has only a certain amount of solubility limit. And therefore, upon cooling, the liquid will transform into two mix of solid phases. So a eutectic reaction is one that will, in which the liquid phase, so one liquid phase consists of a certain percentage of alloy of component A and B. Upon cooling, during the eutectic reaction, two phases of solid solution will be formed. So unlike the isomorphous, when the solidification happens, the end product will only have one phase. This time during eutectic reaction, you will have two phases of solid. So in eutectic system, the two components have limited solubility limit, which means that they form other solid solution or compound above the solubility limit. So for example, if we add component A and B together, but only 10% of component B can be completely mixed in component A. So if our alloy has 20% of component B inside our molten metal, so after it reached that 10% of solubility limit, the other 10% will start to create another type of solid solution. So that is what eutectic system means. So the same with isomorphous system, the construction of the phase diagram is done by constructing the cooling curves of various composition of binary alloy consisting two elements. So here in this lecture, I will use bismuth tin as an example. So 11 material scientists use 11 composition of bismuth and tin ranging from pure tin to pure bismuth in steps of 10% addition of bismuth. So all the composition were measured in weight percentage. So these here are the setup on how they conduct this experiment. So these are the cooling curves of these various composition of alloy of bismuth and tin. So it started with the red color of pure tin, and this purple color here on the other end is pure bismuth. So in between you have various alloy consists of bismuth and tin at different composition. So from here we construct the phase diagram similarly on how we construct the isomorphous phase diagram. So for the pure alloy, it only begin solidification and end at the same temperature. And for the 10%, you can see it represented by this orange color here. For the 20% is this one, and so on. So in the end, we have pure bismuth having solidification happen at isothermal reaction. But here, the difference between the isomorphous and eutectic is that you have this line here. So this line here represents eutectic reaction. So I will talk about this eutectic reaction in detail in this lecture. So this is how the phase diagram of bismuth and tin look like. So you'll probably be wondering, why does it look different than the one I showed you in the previous diagram? So the reason why is that I just flipped them around. So in the previous diagram, we start with tin in this axis and we end with bismuth at this axis. So I want to show you that you can flip the axis around and it will still give you the same phase diagram, but it's just in reverse. So it doesn't matter as long as you know what you're doing. So from this phase diagram, we can see that for pure bismuth, 271 degrees Celsius is where the solidification will begin and end. This is an isothermal reaction. So for pure tin, at 231 degrees Celsius, solidification will begin and end. And this is also an isothermal reaction. So in pure form, bismuth has a rhombohedral crystal structure, while in pure form, tin has a body-centered tetragonal crystal structure. So because of this difference in crystal structure, obviously, only certain amount of bismuth can reside in the crystal structure of tin, and only certain amount of tin can reside in bismuth crystal structure. So this is why they have only partial solubility limit. So before we can further our discussion in interpreting the phase diagram, we need to know what are all these areas and lines in the phase diagram represent. So here, this line here, these two lines here represent liquidus line. So above this line, for solidification process, everything will be in liquid. And as the temperature drop and reach the solidus line, so this solidus line represent where the solidification process ended. So below this line, everything is going to be in solid phase. So as you can see here, there are two types of solid solution, alpha solid solution and also beta solid solution. So this solubility limit can be explained by these 2 points here. So I will start with this point here. So this point here represents the maximum solubility limit of tin inside bismuth. So at this point, at 139 degrees Celsius, the maximum solubility limit of tin inside bismuth is about 4%. So only 4% maximum of bismuth of tin can reside in bismuth crystal structure, and that is at 139 degrees Celsius. As you can see, as the temperature drop, let's say to 100 degrees Celsius, this solubility limit will drop. Means that at 100 degrees Celsius, only about 1% of tin can reside in the crystal structure of bismuth. So this bismuth-rich solid solution is what we call as alpha solid solution. So in this region, we only have alpha solid solution. And let's have a look at this point here. So this point here represents the maximum amount of bismuth that can reside inside the crystal structure of tin. So at 139 degrees Celsius, 20% of bismuth can reside inside tin. So at 139 degrees Celsius, 20% of bismuth can reside inside the crystal structure of tin. So if we have our alloy, let's say with 30% of bismuth. So only 10% and only 20% can form beta solid solution. The rest need to form another type of solid solution. So that's what will be discussed in this lecture. So what I want to show to you, this here is the maximum amount of bismuth that can reside in the crystal structure of tin. And as the temperature drop for, let's say, 50 degrees Celsius, that solubility limit drop. It drops to around maybe 5%. So only 5% of bismuth can reside in the crystal structure of tin. So these two lines here is what we call as solver's line. And the solver's line represent the solubility limit of each of the element inside the other element's crystal structure. All right. So here the alpha solid solution is bismuth rich with some tin atoms reside inside the bismuth crystal structure. And the beta solid solution is tin rich, so it contains a lot of tin atoms with some bismuth atom inside its tin crystal structure. So that is what alpha and beta solid solution. And also you can see these two regions here. You can also see there's another point here. So this point here is what we call as eutectic composition. So as you can see, let me highlight it here. This is a eutectic. We also have this one point here, what we call as eutectic composition. So at this point, when we have an alloy that consists, the liquid that consists 44% of tin and 56% of bismuth, this alloy, this liquid will react like pure metal. So it doesn't have this variation of temperature where it starts to solidify or at one temperature and it ends at one temperature. The solidification begins and ends at one temperature only. So when we have this amount of tin and bismuth in the alloy, in the liquid, what will happen is that isothermal reaction will happen. So the liquid will start to transform to solid in isothermal reaction. So this is what we call as eutectic reaction. So liquid will transform into two solid at that temperature. So this is the reaction of eutectic reaction. So it will begin at 139 degrees when we have 44% of tin inside of our liquid. It will start to solidify at 139 degrees Celsius. Everything will start to solidify. Some of the solid will transform to alpha solid solution and some will transform into beta solid solution. And in the end, we will have microstructure that consists alpha and beta solid solution. So this is what we call as a eutectic point. And then we also have this region here. So the eutectic point for eutectic temperature for tin and bismuth alloy is at 139 degrees Celsius. And we have these two regions here. These two regions consist of alpha solid solution for this region. with liquid in equilibrium, and here we have beta and liquid in equilibrium. So that is that's all the lines, the important lines and area inside the eutectic phase diagram. So now let's have a look at an alloy of bismuth and tin with different composition. So to make us understand about this eutectic system, I will start with an alloy that consists 2% of tin and 98% of bismuth. So this alloy consists of 98% of bismuth and 20% of tin. So what I would do is draw the line representing this alloy. So the cooling curves will look like what you can see here. So this is how it will look like. So the solidification begins as soon as we remove the temperature from the system. So liquid mixture will start to cool down. So above 300 degrees, it is still in liquid form. So as soon as it touches the liquidus line here at 260 degrees Celsius, alpha solid solution will start to form. So the nuclear will start to form, and this is in the form of alpha solid solution, which is the bismuth-rich solid solution. It contains a lot of bismuth atom in the crystal structure of bismuth. And then, as the temperature keeps dropping, everything will transform into alpha solid solution at 235 degrees Celsius, where it touched the solidus line. So at that point, after that point, only alpha solid solution will exist. So until it reached this point here, which I will discuss in the microstructure formation during this process. So this is how you interpret or how you read the phase diagram for this particular alloy. So in this section, I will explain how the microstructure transform for this alloy. So at this point here, above the liquidus line, everything will still be in liquid. So your liquid consists of 98% of bismuth and 2% of tin. As soon as the temperature drops and it reaches this point here, nuclei will start to form. And it will grow bigger, and at that second point here, so this is point number 1, this is point number 2. At second point here, nuclei of alpha solid solution will grow bigger. So we only have one type of solid solution there, which is alpha solid solution. And as the temperature drops, everything will transform into alpha solid solution. So at point 3 here, below the solidus line, only alpha solid solution will be present in your microstructure. But because we have this solvers line here, which represent the solubility limit, what will happen is at point 4 there, the beta solid solution will start to precipitate out of alpha solid solution. So we begin with having a matrix of alpha, alpha, alpha. Because of the solubility limit, we know that only at this temperature here that we are looking at, only about 1% of tin can reside inside the crystal structure of alpha solid solution. So what happened with the rest? The rest will be precipitate out of alpha solid solution. So it will create beta solid solution precipitates in the matrix of alpha solid solution. So this will be beta solid solution. So you might ask, why not just the tin atoms precipitate out, and it creates a pure crystal of thin crystal. So that cannot happen. It will precipitate out with some of bismuth atoms. So it will create a thin rich solid solution, which is beta solid solution. So it creates the precipitates in the matrix of alpha solid solution. So that is how the formation of microstructure for this alloy will look like. Now let's have a look at an alloy with 44% of tin. So this is a eutectic alloy. So we have this alloy consists of 44% of tin and 56% of bismuth. So how does the solidification curves will look like? The cooling curves will look like. So this is the cooling curve. So above 139 degrees Celsius, everything will still be in liquid form. As soon as it touches that 139 degrees Celsius, solidification of eutectic alloy will start to form. And this solidification process happens in isothermal solidification reaction. And as soon as every liquid transforms into solid, which is alpha solid solution and beta solid solution, the temperature will drop again. So this solidification process is similar to pure metals. So this is how the eutectic composition will solidify. So as you can see, eutectic reaction is a three-phase reaction by which on cooling, a liquid transforms into two solid phases at the same time. So in this example, liquid alloy consists of 44% of tin will become a solid mixture of alpha and beta at a specific temperature rather than over a temperature range like the other types of alloy that we have discussed so far. So based on the experimental observations, many eutectic alloy have an alternating structure of alpha and beta lamella. So this lamella structure is a structure that is similar to a layered cake. So this is the image of Sarawak layered cake. So this is how the microstructure of eutectic composition will look like. So one solid phase will sit next to each other. So when you look at the microstructure using microscope, it will look like this one that I show you here. So with the alpha solid solution and beta solid solution sit right next to each other, just like the layered cake. So if we look at the section through this alternating structure during solidification, what we are seeing is a liquid, and behind the liquid are the two phases of alpha and beta solid solution, as indicated by the light gray and the dark gray section. So the alpha phase is a phase rich in bismuth, and beta phase is rich in tin. So if we go to our section in the eutectic diagram, we see the composition of alpha phase indicates by the gray arrow, and the composition for the beta phase as indicated by the blue arrow here, and the composition of the eutectic given by the red arrow. So this gives us the three different phases that are in equilibrium along the solid-liquid interface. So now, in order for the interface to advance, there must be a change in the composition locally in the liquid and solid interface. So in between the liquid and solid interface. So what happened during solidification? So what happened during this solidification process of this alloy consists of 44% of tin, the eutectic composition, is that there will be a process of redistributions of bismuth and tin occurs by diffusion in front of the liquid just ahead of the liquid-solid interface. So what you see in this visual is that we are going to start moving the bismuth in front of the beta solid solution towards the alpha solid solution at the left, and also alpha solid solution at the right of the beta solid solution. And we're going to do this along the liquid solid interface. And similarly, this happened to tin in front of alpha phase. So it will be redistributed towards beta solid solution. So the lamellar structure configuration is the result of the atomic diffusions of bismuth and tin that can only occur at relatively short distance due to supercooling. So this is why it looks like the layered cake, because at supercooling, at temperature, these atoms can only move at a very short distance. So now let's have a look at how the microstructure of eutectic composition formed. So above the eutectic point, everything will still be in liquid. So as soon as the temperature drops to 139 degrees Celsius, which is the eutectic temperature, what will happen is that the alpha solid solution will start to nucleate, and the beta solid solution as well will nucleate right next to alpha. So you will have that nucleation happen. So it's same, you probably have another one in this direction. Alpha starts to nucleate next to beta. So you will have another one, let's say like that. Alpha nucleate next to beta, right next to each other. And this process will keep going. So all the other atoms this nucleus will start to grow and grow bigger at the same temperature, just like pure metal. So this is an isothermal reaction. So at this point, this alpha and beta will grow bigger and bigger until all the liquid is transformed to become alpha and beta solid solution in a lamellar crystal structure. So in the end, when all the solidification, when all the liquid has been solidified, you will have a microstructure consists of this alpha, beta in a lamellar microstructure, just like what I draw schematically here, just like the layered cake. Now I feel like eating layered cake. So in each of the grain, it consists of alpha, and beta right next to each other. So that is how the eutectic composition microstructure will be formed. So this is the microstructure of an alloy of bismuth and tin with eutectic composition. So this alloy consists of 56% of bismuth and 44% of tin. So you can see here, you captured using optical microscope, a lamellar structure of alpha solid solution sit right next to each other. And you can see with the higher magnification, there are two types of solid here. So we have solid 1 and solid 2 formed from a liquid phase consists of this composition. So now let's have a look at a composition that we call as hypoeutectic composition. So hypoeutectic composition is a composition of this alloy that lies on the left side of the eutectic composition, of the eutectic point. So anything on the left side is what we call as hypoeutectic composition. So as an example here, we will have a look at an alloy consists of 20% of tin and 80% of bismuth. So what happened is during solidification, the cooling curves will look like this. So as soon as we drop the temperature of the molten metal, as it reaches 205 degrees Celsius, solidification will start. So what phase of solid solution that will starts to form is the alpha solid solution. So at that point, only alpha solid solution will start to form. And that alpha is what we call as primary alpha solid solution. And within this region, it will start to grow bigger and bigger. And at this point here, it will stop solidified. So alpha solid solution, primary alpha solid solution solidification will end at that point. But as you can see here, if you draw the tie line, so you draw the tie line, at this point we actually still have alpha and liquid. So the remaining liquid, we can find the composition using the tie line. So the remaining liquid has a composition of 44% of tin and 56% of bismuth. So this is a eutectic composition. So at this point here, the remaining liquid will start to transform as a lamellar microstructure because it has a eutectic composition. So the remaining liquid will transform in an isothermal reaction. So the resulting microstructure will have a eutectic microstructure for the rest of the remaining liquid. So that is how the solidification of hypoeutectic composition happens. So now let's have a look at the hypoeutectic composition, the microstructure, how's the microstructure formed. So for this alloy consists of 20% of tin and 80% of bismuth. Above the liquidus line, everything will be in liquid form. And this liquid consists of 80% of bismuth and 20% of tin. As the temperature drops and reach the liquidus line, nuclei of alpha solid solution will start to form, will start to crystallize. And within this region, this nuclei will grow bigger and bigger. And we know that alpha solid solution consists of bismuth rich solid solution. So in our liquid, there will now be a depletion, more depletion of bismuth compared to a depletion of tin. So our liquid will keep depleting of an element because liquids is forming. So at temperature of 139 degrees Celsius, this primary alpha will end its solidification. So at that point, we will have a bigger size of primary alpha, and we will still have a remaining liquid left. And that remaining liquid will now have a composition of 44% of tin and 56% of bismuth. So you can see because of the formation of the bismuth-rich solid solution, the depletion of bismuth atom inside the liquid happen. So this composition now is a composition of eutectic composition. So at this point, isothermal reaction will happen to this remaining liquid. So the remaining liquid will start to transform into a lamellar microstructure of alpha and beta solid solution sitting right next to each other. So at the end, after that solidification process end, so for let's say at 100 degrees Celsius, the microstructure that will be formed, the final microstructure will be a combination of primary alpha with a lamellar microstructure. And this lamellar microstructure consists of alpha, beta next to each other. So you will have something like that as your final microstructure. So this is a primary alpha, and this is a lamella of alpha and beta. So that's what is this indicate here. You have a mixture of alpha and beta with different microstructure. So that is how the hypoeutectic composition microstructure formed. So the real microstructure of hypoeutectic composition under the microscope will look like this. So the microstructure consists of primary alpha with eutectic microstructure. And this eutectic microstructure, if we go for the higher magnification, we can see it consists of alpha and also beta solid solution sitting right next to each other in lamellar microstructure. So how about a composition that lie on the right side of that eutectic point? So we have this eutectic point here. We want to look at the composition on the right side of that point there. So this composition is what we call as hypereutectic composition. So let's take, for example, the alloy that consists 70% of tin and 30% of bismuth. And this alloy, the cooling curves will look like this. So here, above the liquidus line, everything will still be in a liquid form. So this alloy will be in a liquid form. As soon as it touches the liquidus line, which is at this point here, at 187 degrees Celsius, primary beta will start to form. And as we know, beta solid solution consists of a lot more tin atoms compared to the bismuth atom. So it is a tin-rich solid solution. So there will be a depletion of tin inside the liquid at that point. So this beta, primary beta, will grow bigger and bigger within this temperature here. And that primary beta will stop growing as soon as it reaches the solidus line. And as you can see here, at this line here, we will still have liquid. If we draw the tie line, we will still have liquid and also beta solid solution. So the remaining liquid at that point also is going to have a composition of 44% of tin and 56% of bismuth. And this composition is a eutectic composition. So this remaining liquid will now transform into solid of alpha and beta simultaneously in an isothermal reaction. So this is a eutectic freezing at that point there. So the microstructure will be looking similar to hypoeutectic composition. However, the primary crystal now is going to be primary beta. Now let's have a look at the microstructure formation for hypereutectic composition. So for this particular alloy that consists 30% of bismuth with 30% of tin, above the liquidus line, everything will be the liquid, the metal will be in a liquid form. And this metal consists of 70% of tin with 30% of bismuth. As soon as the temperature drops to the liquidus line, which is 185 degrees Celsius, primary beta will start to form. So we will have solid solution of primary beta forming in our liquid. And this primary beta is a tin-rich solid solution. It contains more tin atoms compared to bismuth atom. Therefore, our remaining liquid here will have a depletion of tin. So tin atoms will deplete as this beta solid solution grow bigger. So in our liquid, tin composition will start to deplete and deplete. As soon as it touches this line here, what will happen is that this primary beta, the primary beta will stop growing. So beta will stop growing, and the remaining liquid at that point there, if we draw the tie line, the remaining liquid consists of 44% of tin and 56% of bismuth. So at that point, the liquid now has a composition of what we call as eutectic composition. So we're talking about the remaining liquid. So that remaining liquid will now start to transform isothermally. It will start to transform just like the eutectic composition. So the remaining liquid will start to form lamellar microstructure. So in the end, after that process end, that solidification process end, what you will have in the final microstructure is beta solid solution with a mixture of lamellar microstructure consists of alpha, beta, alpha, beta sitting right next to each other. So this is a hypoeutectic composition microstructure. So the real microstructure of hypereutectic composition under the microscope will look like this. So the dark region here is the primary beta. So that's the primary beta. And you can see here the region where the grain boundary located is the eutectic microstructure. So if I observe with higher magnification, I can see at the grain boundary here, there is an alpha and beta solid solution sitting right next to each other. So as you can observe here, the primary beta is crystallized at the first stage of the solidification, and the remaining liquid, after it reaches the composition of eutectic, will start to form at the grain boundary of this primary beta. So as if you go back to hypoeutectic, you can also observe the same thing. So the last composition that I would like to discuss is this composition here. So this alloy consists of 10% of bismuth and 90% of tin. So the cooling curve for this alloy will look like this. As soon as the temperature being removed from the system, the liquid will start to cool down. As soon as it touches the liquidus line, which is at 215 degrees Celsius, beta solid solution will begin to crystallize. And this beta solid solution will grow bigger and bigger, and the solidification of this alloy will end at around 189 degrees Celsius. So the final microstructure after solidification ended consists only beta solid solution. As the temperature of this metal decrease and decrease due to solubility limit, at this point here, alpha solid solution will start to precipitate out of beta solid solution. So I will discuss the formation of the microstructure in the next slides. So the formation of microstructure begins as soon as it touches the liquidus line. So above that liquidus line, everything is in liquid form, and this liquid form consists of 90% of tin and 10% of bismuth. So as soon as it touches the liquidus line, what will happen is that the crystal structure of beta solid solution will be formed. And this crystal structure of bismuth will grow bigger and bigger. And as soon as it touches the solidus line, everything will transform into bismuth. And at this point here, the microstructure will consist only beta solid solution. But as you can see, as the temperature drops, it will touch the solvus line. So as I explained in the beginning, the solvus line represents the solubility limit of for this solvus line, it represents the solubility limit of bismuth atom inside the crystal structure of tin. So at that point, at 100 degrees Celsius, what will happen is that the crystal structure, because the temperature is dropping, you imagine even yourself when the temperature drop, you will start to consider like shrinking yourself. All right. So that's what happened to the crystal structure. It will start to shrink. The bonding between the atoms will start to shrink. So what will happen is that the atoms of bismuth is going to be squeezed out of the crystal structure of tin. So when that squeezing of the bismuth atom happen, some tin will also be squeezed out, and it will form a precipitate of alpha solid solution outside the beta solid solution. So the microstructure, after it passed that solvus line, will look like this. So we have a beta solid solution matrix. So beta, beta, but with some precipitate of alpha on that matrix. So this is alpha phase. So the final microstructure at room temperature will consist beta solid solution with the precipitates of alpha solid solution distributed on the microstructure. So under the microscope, this is how it would look like. So you can see the regions of the dark region here are all beta solid solution. If I observe under higher magnification, I can see the alpha phases precipitate out of this beta solid solution. So similar to the isomorphous system, I can use tie line to determine the phase composition at any point in this phase diagram here. So let's take, for example, the alloy that consists of 70% of tin and 30% of bismuth. So I want to know what other phases exist at 150 degrees for this alloy. So what I need to do first is to draw the line to represent this alloy. So the red line here represents the alloy of 70% of tin with 30% of bismuth. And next, what I need to do is to draw the horizontal line passing through the temperature axis of 150 degrees Celsius. So from there, I know that at that point there, at this point here, is the point that I'm talking about, and it lies in the area where liquid and beta solid solution exists. And now I want to know what is the composition of liquid. So what I can do is to draw the tie line passing through the liquidus line. So this horizontal line passing through the liquidus line, and from there I will draw this vertical line passing through the composition axis. So from there I can conclude that this liquid phase at this point, at this temperature, consists of 49% of tin and 51% of bismuth. And what is the composition of the beta solid solution? At that point, I can draw this vertical line passing through the composition line, and I can conclude that beta solid solution consists of 83% of tin and 17% of bismuth at that particular point. So similarly, using lever rules, we can also determine the phase fraction of each of the phases that we are interested. So from here, just then we know we have this liquid phase and we have this solid phase. Now we want to determine if, let's say, I have 100 kilogram of alloy. At that point, how much alloy has turned already into solid and how much percentage that still remain as liquid. So you can use lever rule to get this percentage. So similarly with the isomorphous system, using the lever rules, we can get the mass fraction for each of the phases. So at this point here, at 150 degrees Celsius, we have liquid and beta solid solution. Using this equation, we will get that at 150 degrees Celsius for this alloy here, 61.76% of the liquid has already been transformed to solid and the remaining is still in liquid form. So imagine if you start with 1000 kilogram of molten metal at 150 degrees Celsius, about 617.6 kilogram has already transformed into solid and the remaining still in molten metal. So an example of application where you can use phase diagram is when trying to choose soldering materials, soldering composition. So for many years, plumbum tin alloy has been used as a soldering material for copper pipe. So this is a copper pipe, and these soldering materials consist of alloy of plumbum with tin, and this is the phase diagram of this alloy. For many years, they have used this composition as the soldering materials. However, they realized that if they look at this phase diagram, if they shift, when they use the eutectic composition, you can see that this solidification happen in one temperature. So it will begin and end at that temperature. So you don't have actually room to adjust the pipe while you're soldering them. So it will start to solidify at one temperature and end. So it starts to harden straight away when it reaches the temperature of the eutectic temperature. However, if they choose a slightly off eutectic, which is around that point there, what they can observe is they will have this slimy region here. So solidification will begin at one point and it will end at one point. So the metal won't be hardened all at the same time. It will take some of the liquid will start to solidify at certain temperature and some will solidify at another temperature. So they will have room to adjust the copper pipe while they're soldering this pipe together. So that is one example on how we can choose which composition that we need to use for each particular application. So another example is for electrical solder. So this is also use the same type of alloy, which is plumbum and tin alloy. But in this case, they will need to use eutectic composition because it is important for the solder to solidify all at once. So that ends our discussion today. So in summary, we have learned that in a eutectic reaction, a liquid phase transforms isothermally to two different solid phases upon cooling. And this happened because there are no complete solubility limit between the two elements. Instead, there is only a limited solubility limit of each component in each other. So there are four kinds of microstructure that may be developed for the equilibrium cooling of alloys belonging to the eutectic system, and this has been discussed in this lecture. So thank you for listening. I know this topic might be a little bit hard for you to understand, especially when you are not in materials major. Even materials major has problem with this topic. So try to listen to what I said multiple times. Try to understand what I was trying to say in this video. And if you still cannot understand, don't be shy. Talk to me and ask me to explain it again. Take your time, do a little bit of exercise that I am going to put in your tutorial. Try to solve it and we will discuss that in class. Thank you.